Hi everyone, the purpose of this video is to introduce spectrophotometry, which is an important lab technique we use a lot in this class. Spectrophotometry is a type of spectroscopy, where spectroscopy is just the study of how light and matter interact, and spectrophotometry is about measuring quantities of light as they interact with matter. In this case, it's going to be about light passing through what we call a cuvette, which is just a small container, usually 1 centimeter wide, and you can see the amount of light that's coming in there, labeled as IO, or the initial intensity of light, is much greater than the amount of light which is exiting. So some of the light is absorbed by the solution. And you can see that light is pink. We can use different colors of light depending on what solution we're analyzing. Here's the spectrophotometer apparatus we'll use. Now this is a scaled down spectrophotometer called a colorimeter. There's only 4 wavelengths of light you can choose to use here. A spectrophotometer will have all sorts of wavelengths of light, a whole spectrum, sometimes even into the UV or infrared parts of the spectrum. But this will do for us. A very common sight you'll see in this classroom throughout the year is what we call a serial dilution of a particular solution. Let me show you what that looks like. Here's a serial dilution of a compound which is blue in aqueous solution. The first one here is 1 molar, then 2, and 3 molar, 4 molar, and 5 molar. So I wonder what the concentration of this sample is. Well, using just the naked eye, you can probably see, I think it falls maybe somewhere along here. But the spectrophotometer can do a better job of analyzing how much light is passing through and telling us what the concentration is. Here's how we'll use a spectrophotometer to generate a Beer-Lambert law graph. You may remember using a colorimeter in the fall, and we reasoned about the fact that I'm going to use a 635 nanometer wavelength red light in order to analyze this blue solution. The first thing I need to do is sort of teach the spectrophotometer what 100% transmittance looks like, or zero absorbance. I do that by calibrating the spec at the particular wavelength I want to use. Once that red light stops flashing, it's calibrated and it's set to use. So we'll go ahead and set it up to record the absorbance of each of these different concentrations in our serial dilution. I've set the lab quest up to record as events with entry, so it's only going to record an event when I tell it to. Here's the first solution, which is 1 molar. I set it in the spec, and I tap keep once the absorbance is steady, and it's going to prompt me for the molarity. The molarity of this solution is 1. Now I'm going to go ahead and put the next solution in. You know the next solution has a molarity of 2. I'll tap keep now that it's stabilized and enter this molarity. The molarity of the second solution is 2. Now you can see there's a linear relationship starting to form. I'll go ahead and do the next 3 solutions. So there, I've put in all the other concentrations, and you can see it makes sense. The absorbance is getting higher and higher, and that's because the solutions get darker and darker as they get more concentrated. So how does this help me find the concentration of an unknown solution? Before, I was trying to compare where along this spectrum of darker light colors this unknown would fall. And we have a graph here that shows us how molarity is related to absorbance. Let's find a curve fit for that graph. It looks to be linear, so I can have LabQuest generate a linear curve fit, and then I'll use the equation for that line to calculate the concentration of this unknown. Now that I have that linear relationship, I can go ahead and measure the absorbance of this sample. Let's see what the absorbance of this sample is. I'm going to take the blank out and put this in. I had it somewhere in between these two before. Let's see if I was right. The absorbance is about 0.268. Well, where does 0.268 fall on my graph here? It's about halfway up this axis, it looks like, and I could graphically determine this, or I could simply do the calculation by using this y equals mx plus b equation, and I can find out what the concentration of the unknown is that way. Now the LabQuest has given us a simple y equals mx plus b relationship, and this is what is essentially going to boil down to Beer-Lambert law, or Beer's law. The equation as it's presented here looks a little bit different than y equals mx plus b. Instead of Y, we're using the letter A for absorbance because that's our Y-axis. And instead of X, we're using the letter C for concentration because that's our X-axis, the concentration of the solution in molarity. The term A here is the slope of the line, the letter M. And the term B is simply the path length that the light travels through. And for a standard cuvette, that's always 1 centimeter. Since it's 1 centimeter and B is equal to 1, this equation can be simplified as A equals AC, or absorbance equals the slope of my line multiplied by concentration. So if the equation can be simplified to A equals AC, I can solve for concentration. The uppercase A here is absorbance, and the absorbance of my unknown sample was 0.267. The small letter a here is the slope, and the slope of my line here is 0.0772 approximately. There we go. And so I can solve for concentration. The concentration is simply going to be absorbance divided by slope. Now, absorbance divided by slope in this case would be 0.267 divided by 0.0772, 3.45. It looks like I was right. This sample was somewhere in between 3 molar and 4 molar in concentration. That's how Beer's law allows us to use a spectrophotometer to measure absorbance and calculate concentration. Now we'll be looking at this relationship and analyzing the concentration of aspirin in a tablet.